Good morning, good afternoon. We are very excited again to have another Amazon webinar. So this is the fourth webinar. So it's a continuation of the series we have been doing. We've had hundreds of participants from all over the world. So I think until today we have had around 400, 500 participants. And usually the reactions are very, very positive. And this is why we keep doing it. And we keep reinventing new content. So also this webinar, if you're attending for a third or a fourth time, will be completely new content. Very excited to present it to you. This webinar is focused on removing the uncertainties around secondary effluents. Ozonation, so there's a lot of applications in that area. There's a lot of growing potential. And there are a lot of challenges. And this webinar is really focused on that. So today's objectives, this is where we will start with. Why are we here? What do we want to obtain? So let's first go into the context. So we have been building Amazon, which is a process simulation model for advanced oxidation and ozonation. And it is being increasingly applied at a global scale to optimize plants, to operate plants, and to design and scale up all of these things. So we will show a lot of examples there. And what are the objectives today? Well, we want you to go home, or virtually go home, let's say, with a lot of new detailed process insights that are directly practically applicable for you. And second, we also want you to understand the practical application potential of process simulation because it's largely unknown in the ozonation or advanced oxidation fields. What is the format of today? It's a hybrid webinar. There is a lot of interaction and dynamics here. So we will go to live demos. We have a couple of slides with some more theoretical background, and we have live answering of questions. So if you have questions, please don't wait until the end. Please write them down in the Q&A. If you hover over your screen, you see a Q&A button. If you push that, you can ask questions there. Please do not ask questions in the chat window. So you can also choose to disclose your name when you ask questions, or you can also pose questions anonymously. After the webinar, there will be a short questionnaire. Please fill it in because it's hugely valuable. And this is how we keep improving these webinars. Okay, so we will not be repeating a lot of the other webinars because, a big fraction of you is coming back, and that would be very, very boring. So in case you would really want to dig in further on the content and want to really discover what we all have been talking about in the last couple of webinars throughout the last 2 years, you can find all of the recordings and content at our YouTube channel. So youtube.com/c/amteamtv. That's the link. And we have a dedicated Amazon playlist there. A lot of movies, and you can also, of course, go to our website, amteam.com/Amazon, to learn more about what Amazon is about. A lot of snippets and videos and things like that. So, okay, let's go to the people. Who are we? This is AM Team. This is our current team. All passionate modelers, passionate people, a lot of people with engineering backgrounds, and we are a company focusing on process simulation for the global water industry. So we are helping end users, consulting firms, technology developers with accelerated optimization, design, and scale up of technologies. So we are working at the process site. We are working on multiple water and wastewater treatment unit operations. Ozonation and advanced oxidation is one of them. And we have been, of course, doing a lot of work in that area. So this is the current team today. So the people you see highlighted, I'm Wim Oudenaert. I'm CEO and co-founder at AM Team. And I did my PhD actually 10 years ago on this topic of ozonation. So it's a topic very close to my heart. Then we have, of course, Roberta Muyo. She is advanced simulation engineer at AM Team. She's zooming in from Italy. And she has been working on Amazon for the last couple of months and years. And then we have another Italian colleague, Giacomo Bellandi, also working on Amazon for years. He's senior simulation expert and has a lot of process modeling knowledge, actually. We have then also Peter Vlasgaard in this call. So he's solution engineer at our company and specifically serving a lot of customers with Amazon solutions. So he's providing a lot of the services and developing the solutions for the customers. And then we have Charlotte van Isegem. She is our marketing manager, and Charlotte is coordinating this webinar and also monitoring the Q&A. So she will bring questions live to the forefront. What is the why of our company? Before we go to the content, it's always good to start with why. Well, our company challenges the status quo in process engineering for optimal use of resources. The resources can be very wide. It's not only the chemicals or the energy, like let's say the standard resources. We are also talking about man hours, man days, man months, saving a lot of time. Maybe you have to build less pilots. Maybe you can skip a couple of experiments. So resources in this context is very, very wide. So we try to limit that by bringing simulation solutions to the water industry. Okay, let's go into the content and start with effluent ozonation. So this is a map you see here. It's not a world map, it's Europe and the US. And this is the full-scale status in 2014. This is 2014 because we published a paper back then with the whole status and also the regulatory updates. So you can ask us for the paper after the webinar, just send us an email and we will send it to you. But you can see back then, Europe plants were emerging, especially in Switzerland, of course, and in the US as well. But there is a big difference in applications because if you look at the bullets here, they are focused on trace organic removal, which is especially Europe. And then the squares are focused on disinfection or are more water reuse related. And this is, of course, the big trend in the US. Similar applications, like how the plants look like, but it's very, very different in terms of what you want to achieve. If we just look at what is happening, it's kind of an exponential growth with full-scale ozonation plants. In Europe, it's really growing rapidly because micropollutants are being removed at a rapid pace. And in the US, of course, you have a lot of emerging water reuse projects. In Switzerland, a lot of regulation is there. In Europe, they have a watch list. And in the US, they have a very strong, very well-developed water reuse regulation, especially in California and some other states. Good, I will now give the floor to Peter, my colleague, and he will be zooming in on Amazon.
All right, thank you, Wim, and hello, everyone. Yeah, like Wim already explained, ozonation of secondary effluent for micropollutant removal is quite new for all of us. And that's also actually why we developed a tool, a simulation tool, Amazon, that can model ozonation processes and advanced oxidation processes to predict micropollutant removal and bromate formation based on dynamic data. How does it work? What does it look like? Actually, what you can see here on the left side of the screen is the virtual ozonation plant. So this is a reactor, an ozonation reactor. And yeah, what comes out of the model are actually the results of bromate formation and micropollutant removal in real time. So this is 20 days, and you see dynamic simulation of bromate formation. And we can also do this for all micropollutants that are available in the model. How does it work? Well, in the background of this model, all the kinetic reactions from ozone and other, like hydroxy peroxide are taken into account, and the reactions with organic material and inorganic material like nitrites and ammonia are all modeled in this tool and are all taking place at the back. And with these reactions, we can predict the micropollutant removal and the bromate formation in real time. We are also very proud to say that we won the Digital Water Award for this tool. And we use this tool to help designers and operators of ozonation plants with a better performance system. Let's move to the next slide. Now, I already briefly explained what Amazon is and how that it worked in a nutshell, of course. Now, where can it help you all? So in this webinar, we have technology vendors present, we have designers present, and we have people from the utility present. So people who are going to operate these plants, process engineers, for example. Now, actually, Amazon can help you in removing the uncertainty in an ozonation process, actually during the whole cycle of an ozonation process. So from feasibility study over the design to the operation of such a plant. For example, in technology selection, usually people perform pilots for this, and pilots are very time consuming. And measuring micropollutants removal and following this up is also very expensive. By applying Amazon as a virtual pilot with your data, your dynamic data, we can help you in defining the optimal dose for your micropollutant removal, define what is the risk of bromate formation, and give you insight in the operational costs of such an installation. So this can save you a lot of time in the future design and can save you a lot of money. If we go to a design phase, we have a conceptual design and a detailed design phase. And in these design phases, also Amazon can help you in defining the optimal reactor size. It can help you in selecting the best injection method of your ozone, which dosing strategy are we going to apply, and then more into detailed reactor design, we can combine the Amazon model with computational fluid dynamic simulations to optimally design your reactor and to look at the effect of the mixing on the bromate formation and on the ozone transfer efficiency, for example. So this helps you designing a performance system and without blowing up the investment costs. So we can also reduce the investment costs to have a performant installation. Then in the operational phase, so once you have a full-scale installation or a demo plant of an ozonation plant, we can, with the help of your basic online data or offline data, with basic sensor data like flows, DOC, ammonia levels, and all of these parameters, together with the Amazon model, we can actually predict the micropollutant removal and the bromate formation in real time. So that's what we call a digital twin. Now we've seen these three types of applications. It's time for a poll. I see it already appearing on my screen. So indeed, which application is most interesting for you right now? We are very curious. We don't see the results yet. All right. Okay. Yeah, we see a little bit less in the detailed design, but yeah, I would say it's well divided. So I think we have a good mix of people here in the webinar, and we will also tackle actually the three main phases in going from a feasibility study to a full-scale installation. So that's perfect. Okay, we have 4 topics for you. Let's start with the first topic. It's actually the impact of the importance of the water matrix and the uncertainties around it. So yeah, the water matrix is actually the starting point for designing a full-scale installation. And each wastewater treatment plant has a specific water matrix. It's always something else. So target contaminants are of importance, of course. The organic material, the inorganic material, nitrite concentrations, ammonia, alkalinity, pH, all these kind of parameters have an important effect on the overall design, on the future design, on the feasibility of your plant, of your ozonation system, and on the operations. We can talk a lot about all these different parameters and what is the impact. So we are not going to go into detail on this today, but as you can see on the screen, there's a QR code. if you scan this QR code, you will be redirected to our YouTube page, where we have a specific channel on ozonation and Amazon, so where there is a lot of content on this. So yeah, please follow these links or follow this QR code, and then you will have more information on this. But what I wanted to tell about the water matrix is, yeah, like I already said, different plants have different water matrices, and this has a very big impact on your overall design. What we can see here are actually two graphs. One, so on the x-axis, you see the ozone doses, so grams of ozone applied per gram DOC. And on the y-axis, you see the ozone exposure and the radical exposure. And these exposures have an impact on the performance and the micropollutant removal. What you see here is that, for example, for 1 gram ozone per gram DOC, for all these different plants, this has actually a complete different ozone exposure. So you apply the same dose to different wastewater samples, and you see a completely different ozone exposure, and you see the same with radicals. So this has a very big impact on the overall performance of your system and on the design of your system. So it's very important to have this water matrix right and to draw the right conclusions from this water matrix. And next to this, water matrices are also dynamic. So this is just with one sample, but yeah, a water matrix is something dynamic and it changes over time. So it's very important to have this in your mind. So that's actually key point number one. The matrix makes the design and operation of such plants very, a big challenge. That's why when we perform virtual piloting with the Amazon model, we combine batch test data. So we send 1 or 2 samples to a lab, and we see at the ozone decay, the ozone depletion. We look into this, and we combine this with your dynamic data of your plants. So the flows, the DOC, the ammonia levels, we combine these two together with the process conditions of a future plant. And then we are going to look at what is the optimal dose. What will be your micropollutant removal with different ozone dosages? So the impacts of the dynamics are taken into account. And we also look at the impact on bromate formation. We can look into the aspects of different injection systems. So here we performed actually 9 dosing scenarios in 6 weeks. So yeah, it can really help you to save a lot of time and money instead of doing a real physical pilot. So now we talked about the water matrix, starting point. Topic 2, going from batch tests or pilot tests to a full-scale installation. There's a lot of uncertainty in this process because you scale up. So what we usually see is nowadays, as a starting point, people still use sometimes just batch tests, or they use a pilot test that is performed in a lab or on site to go to a full-scale installation, or to make a design for a full-scale installation. And how this batch test is performed, or the conditions in this batch test, have an important effect on the results of this batch test and on the conclusions you draw from this batch test to your future design. So it's, you need to be aware of these assumptions from these tests and know what can be the impact on your overall design. Roberta will show you in a live demo a little bit more on this topic and what is the importance of these batch tests and what is the sensitivity of these batch tests on the overall performance of your system. So now I give the floor to Roberta, and we are going live to Italy.
Yeah, thanks, Peter. Hello, everyone. And so let's see in one simple but meaningful example, where is the impact of, for instance, human factor when we are dealing with batch experiment. So imagine we are in the lab and we are using a certain ozone stock solution. We are pouring this ozone stock solution in the beaker containing 1 liter of our secondary effluent sample. So we are dosing 0.25 liter of stock solution with a certain ozone concentration, in this case 50 milligrams per liter, and we'll see the effect on the injection speed. So let's first assume that we are injecting ozone in the ozone stock solution within 10 milliseconds. So a very fast ozone injection speed. Let's see what happens in terms of ozone profile and ultimately in the bromate formation. So what we can see is that there is, if we zoom in, a big jump in the ozone concentration in the beaker, because we are injecting ozone in only 10 milliseconds. Then what we can see is a drastic drop within the first seconds, 3 point something seconds, and then a gradual decrease in the ozone concentration. In terms of bromate formation, we can see the bromate is being formed within the very first seconds. It's already 18 micrograms per liter, and then it's gradually increasing till the end of the experiment, 28 micrograms per liter, due to the presence of residual ozone concentration. But now let's see what happens if we increase the injection time. So we are now injecting the ozone stock solution, same volume, same concentration within 2 seconds. So let's see what happens again in terms of ozone concentration and bromate formation. So what we see is that we reach a lower ozone concentration in the beaker, in the liquid phase. Why? Because meanwhile we are injecting, the ozone reaction are happening. So at the same time, the ozone is being consumed. So we see again a same pattern with a drastic drop and a slower ozone decay afterwards. And in terms of bromate formation, we can see that bromate is again formed within the first few seconds, and we reach 13 micrograms per liter after 3 seconds, more or less. And ultimately, at the end of the experiment, we reach 24 micrograms per liter. So we have seen within 10 milliseconds, we're forming 28 micrograms per liter. Now within 2 seconds of injection, we are producing less bromate, 24 micrograms per liter. Now let's see, last example, what happens if we inject ozone within 40 seconds. So let's see the results now in terms of first ozone residual. So the ozone in the liquid, the peak of ozone in the liquid is now after 40 seconds, because we're injecting ozone within 40 seconds, and is 3.5 milligrams per liter of ozone. And then the ozone is being consumed by the water matrix. In terms of bromate, we can see that now bromate increases smoothly, let's say, within the first seconds, and then it reaches bromate formation at the end of the test of 14 micrograms per liter. So what conclusion we can draw from this? If we inject ozone, the ozone stock solution very fast within a millisecond, which is rather impossible, we end up with a higher bromate formation. But if we inject ozone in a longer period of time, 40 seconds, we can actually see a bromate formation up to 50% lower. So this is very important to know, to evaluate the results of a batch experiment. It's very important also to know this detail about the human factor and the operation of such tests. Thanks. I leave the floor again to the presentation.
Thanks, Roberta, for sharing the demo. Was very nice to see how sensitive batch tests are on how they are performed. So the reason why we highlighted batch tests here is because they are the extreme example illustrating how sensitive not only the matrix, but how you set up piloting or batch lab experiments are to the conclusion. So it's all about the assumptions. How long do you dose? How do you mix? And that's very, very interesting, because if you obtain a certain bromate level in the lab, you might use it to extrapolate to full scale, but that might be an issue in a later stage because it's not really representative. And we can actually take it one level further. And what is currently on this slide has never been shown before. And you will also not find it in academic literature. So this is really like the first time ever we showed this. And we will use them a lot, these insights, because they are quite disruptive. I mean, what we are doing now is we are coupling a CFD model, which is a 3D model, with the kinetic model. And we are simulating with a CFD model exactly the same batch test as the one Roberta has shown. But the difference is we will look into 3D. So what you will be seeing here is movies of the local concentrations of ozone, bromate, and diclofenac, one of the micropollutants. So red means 100% diclofenac, and if the color starts disappearing, we are removing it. And ozone, of course, is dosed at this site. You can already see it happening. So let's look, if we dose ozone, what happens with the ozone level in this batch test. So we see a cloud, a local cloud is going around. And in this test, we are only visualizing the first 3 seconds because a lot of things happen in the first 3 seconds. So you have seen that actually you have a local cloud of ozone, which is actually even in a little batch test of 200 milliliters, not very well mixed, but the kinetics are way much faster than the mixing. And this brings us to bromates. If you see where the bromate occurs, it all happens where you add the ozone. So I will play it again, and you have to pay attention to this red spot that will appear right at the beginning of the movie. So I play it again, and you can see there's a red spot, which is a huge local bromate concentration that happens because of the local kinetics with the local high dissolved ozone levels. If you look at it from the top after 1 second, you can see that you have a red cloud of bromate being formed in your system, driven by the local high ozone concentration that is very poorly mixed, but all of a sudden introduced in your beaker. If you look at diclofenac, of course, we have a removal. So you start seeing a cloud that starts, let's say, eating away the diclofenac, which is, of course, the ozone. With this system, of course, it's a bit at a lab scale, but you can just do it exactly at full scale, which we are actually doing at full scale plant design. And this brings us to, actually a new insights of how these systems can be better designed. So you have to really consider first, at a small scale, how you extrapolate results from it. And second, if you design a full-scale plant, you really have to consider these kinetics. So the key point, what we wanted to address with this section is batch and pilot tests are meant to gather information for a future full-scale, but batch and pilot scale designs are often not representative to make this extrapolation. And that is really a key message we wanted to give here. You have the matrix, okay, you have your ozone dose, that's fine. But please bear in mind that how you set up the tests at smaller scale are equally important for your conclusions. And we have seen really a lot of practical insights there. And we have talked to a lot of practitioners that have witnessed this with extrapolations. So be careful, your assumptions matter. That is the key message here. If it's not clear enough to you, we of course invite you to ask questions, and we can always clarify. Also, at the end, we have time for questions.
I'm sorry to interrupt before we continue, but we in fact already received a question related to this. So Sri asked us, can you comment on the contact time difference from lab scale to full scale and how that is addressed by the model? Could you expand on that? Yes,
yes, indeed. So if I understand the question correctly, it's time related. So yeah, the model is a dynamic model, so it takes into account the time. So you already saw it in the last slide. You see reaction as function of time. So it means you address a certain volume to a certain scale in the model, and you address, like you put in a certain flow rate. The volume and the flow rate give you a certain time. And of course, together with reaction kinetics with a certain speed, give you a certain conversion or concentration as function of time. And then if you go to a larger scale with a lower flow rate or so, actually these things are automatically taken into account. Yeah. Sri, if I didn't answer it correctly, your question, just ask a new one and we can dig deeper on it. But thanks for your question.
We have a second question coming in, Wim. Sorry.
Very good.
So Mohammed asked us, what's the main ways for scaling up ozone process in large scale?
Yeah. Well, there are various ways here, and yeah, of course, we start at smaller scale, but we typically start simulating at small scale, which gives you a lot of insights on the assumptions. And then, of course, you can extrapolate. But just bear in mind, if you have a bromate level of 60 micrograms per liter at lab scale, that this might not at all be the case at full scale. You might have 10 or 20. Let's say small scale experiments, for example, we used to have a certain worst case bromate formation. And by modeling it like it is done in the reality, we come to a very good model calibration, and we use the model to make the scale up. So we use the model to make the scale up. That is actually how we help a lot of customers together with design teams. Good. If we first tackled the matrix, then the uncertainty with scaling up, and now we will go to design. So if you look at design, this is a figure we have shown in one of the last webinars. These are the 4 big categories of factors that drive the ozonation process performance and cost. So performance means removal, but also bromate formation, transfer efficiency, things like that. It's all about process parameters. How do you operate your process? Gas, water flow rates, dosing locations. That's operational. On the other hand, as an engineer, of course, you have to design it. So it's all about the reactor, the transfer equipment you use. Of course, we already talked about it. You have the water matrix as well. And then you have the human factors, of course, the operator that is operating a plant, or how do you operate it? If we zoom in on these two, these are the two you design for. You can choose as an engineer, and you can actually impact. And we will now go to Italy again, to our colleague Giacomo, and he will be demonstrated that actually your choices matter. So which choices you make here really, really matter. So Giacomo, the floor is yours.
Thank you. Thank you. Let me share my screen and I'll bring you to my laptop, in which you can see a full-scale installation represented with a general injection system here. That can be diffusers, can be side stream injection or hybrid systems. And then you have the flow going through a couple of reactors. This is an installation of a total 100 cubic meters. And then there is an influent going in, which we can run dynamically, an influent going in with a couple of days of dry weather, and then a rain event that will hit the plant in the 3rd day. At a certain point, you will see our bypass will take action and avoid that the whole gigantic influent goes through the ozone installation, but just the maximum capacity of the installation. Now you see the flow rate going through our plant, the daily dynamics. We are passing through day 2, and now we can check the HRT of our installation, which is rather high. It's 37 minutes in total, almost 40 minutes. And now the rain event is hitting our installation. So a maximum of 2000 cubes, it's passing through the plant. So what if at this point we decide, okay, so we have some room with HRT, but what about to reduce the installation? But how about our residuals of ozone? Now, if we look at the residuals of ozone, we already see that a reactor 2, we don't have any, even though we have a big flow coming through, and reactor 3 actually is not in use. So we could actually sensibly reduce the size of the installation. Here I'm making just a change, reducing the whole installation volume by 30%. And then we can continue the simulation here, and then we can watch how that reflects in terms of micropollutants removal. Here we see that the average removal doesn't change significantly. Why? Because we still have room for complete exposure to the dose that we're inputting. Here we see an increase in the removal due to the rain event, which is lowering the strength of the water and then making the life of ozone and radicals longer. And now we can see that the rain event, in which we had a minimum HRT of 7.2 minutes, is now causing another peak event is causing the HRT of 5 minutes, which is completely reasonable if we look at the residuals, which are very reasonable, especially at the effluent of our installation, because we are far below at any detection limit in this case. So, and with this, we can go back to the presentation, and I'll show you later another demo. Thank you.
Thank you, Giacomo. In the meantime, we got another question coming in from Mohammed, who is wondering if we consider resident time distribution model to evaluate the behavior of fluid inside the reactor, or using CFD model.
Yeah, this is a perfectly timed question, Mohammed. Thanks, Charlotte, for bringing it forward. Because this brings us to the CFD slides. And yes, full-scale reactors have non-ideal dynamics. So mixing is very complex. You always have some short-circuiting, some dead zones. For example, in this reactor, you can see some rotating zone. I agree, it's a poorly designed reactor, this one, but we are showing a quite extreme case in this case. And yes, if we model full-scale plants, we try to, usually we were involved in the design stage where we use CFD to help designing the reactor. Based on exactly the same model outcomes which we used for the design, we transfer that to the environment Roberta and Giacomo have shown, and we construct a better model with it. So we have some methodologies for that. And yes, so this allows us to include residence time distributions in it very realistically. And this is the best of both worlds, because you still have a dynamic model that runs very fast, but still you have the realism of a CFD model in terms of hydraulic representation. Yeah, we are not going into this methodology in this slideshow, but if you want more information on that, you can always drop us an email. So talking about CFD, well, the message we want to give under this point is your choices matter, but you can really impact a lot yourself. So you can really impact a lot in the design stage. You can use, for example, the sizing. If you look at this reactor, you see the ozone residuals going through a reactor under and over the baffles. In this case, yeah, for example, 40–50% of your reactor has almost no ozone, or no ozone actually. And if this is happening at an event where a lot of ozone was dosed, you can ask yourself the question, can we maybe not design it a bit smaller here and still account for the peaks safely? That's one thing. And then, of course, you can start detailed designing. Where do you put baffles? Can we further knock down bromates? Where should we add peroxide? Or how to improve the ozone dissolution? You can use CFD for that. In this case, you can see the impact of hydrodynamics on bromate formation in a full scale. And if you don't care, if you don't really pay a lot of attention, you might have some hotspots of bromate in your installation. You can not only, well, it's not only reactor related, you can also talk about equipment. For example, this is more of a pipeline flash reactor with a static mixer. You can look at the dissolved ozone going through, or you can also look at the Venturi pipes in detail to better design equipment. So your choices really matter as long as you understand the impact of your assumptions and also the matrix, take it into account. But we are 2021 and a lot of tools are at our disposal. Good, let's go to the uncertainties with regard to operation. Peter, I will give the floor back to you.
Right, thank you, Wim. Okay, so we already talked about the water matrix, feasibility studies with virtual piloting, and about design. Now let's talk about what when an operation is when an installation is in operational mode, and when you have to operate a full-scale ozonation plant. Water matrix, again, very important. What you see here is a graph simulated by our model of the bromate formation in a time series of 40 days. You see a lot of dynamics. So you have higher peaks, you have lower values of bromate. And if we look at, for example, the input parameter ammonia that we also take into account in our model, we can see there's a direct link. So when your bromate levels are dropping, this is clearly caused by an increase in the ammonia levels. And we see actually the opposite when you have very low ammonia levels, which can happen after your aeration is switched on to its maximum level. Then you can have an increase in your bromate formation. So you clearly see that the ammonia is a very important parameter in controlling bromate, and that dynamics are also very important once you are operating an ozonation plant. And yeah, with the model, we can predict these dynamic variations in your micropollutant removal and your bromate formation, and we can see what is causing this. And that's how we can help you in smartly controlling your ozonation plant. We will go to Italy again for a demo. So Giacomo will show you some more of this.
Yes, welcome back. Let's directly go to my screen and have a look at this data. So these are like samples. Imagine these are your samples. And you took samples and measured bromate at different times. So this is a period of 7 days or something. So, but the question is, what happens in between these days? Are we missing peaks? Are we are this like a composite samples? Are this grab samples? So it's difficult to say because in the meanwhile, between one point and another, all kinds of dynamics in the plant will go on. So the effluent has its dynamics, as we have seen. We have the flow changing. We have UV absorbance changing, so the load of organics is changing in time, and also the ammonia, as we have seen, is changing. So as you can see here, there is a peak in UV absorbance, which is brought by the washout of the sewer. So and right after that, there is a dip in ammonia as well, so, due to the upstream biological plant, which is probably over aerating as a response to the ammonia controller, and also at this other peak, ammonia is lacking. So what is happening actually in between this bromate measurements, offline measurements, and we can pass the model through that. We can simulate these days and see what happens in the dynamics. Actually, this huge peak and this one were generated by specifically low ammonia levels at certain moments, as we were saying, as a result of the dynamics of the effluent, so the concentrations that are incoming to the plant. So there is an initial washout of the sewer, but then there is also a dilution effect brought by the rain event. And then also the operational settings of the upstream biological plant, which is over aerating and removing more ammonia than necessary, which is resulting in these peaks. Now, if we run the same simulation with, let's say, a dosage of peroxide, then we can sensibly lower the bromate formed, and we can monitor this throughout the installation. There are moments in which this the peroxide dosage is more effective due to specific conditions of the influent composition, and other moments in which it would not even be necessary to dose peroxide, and then we can even save chemicals and operational costs. But on the other hand, we can also, as we has been speaking about the ammonia, we can also increase have more fancy controllers and try to control bromate, optimizing the aeration at the upstream plant. So making sure there is a minimum ammonia concentration coming out, that we are not exceeding, of course, the effluent limits, but we can still have a sufficient action of ammonia on hyperbromous acid. And that will result, as you can see from this purple line, in a shaving off of the peaks that I was talking about before. So in these cases, specifically at 4.5 days and 5.7 days, you can see that the peaks are shaved off just because we optimized the upstream wastewater treatment plant controller to ensure there was just enough ammonia to avoid the peak bromate formation. Yeah, with this, I thank you, and then I give back the screen to the presentation.
All right. Thanks, Giacomo, for this interesting demo. All right, so yeah, Giacomo clearly indicated the power of these dynamic simulations, and this can help you in understanding your system even better and the impacts of these variations on bromate formation and micropollutant removal. The previous graph I showed you was from a plant that was not built yet. We also applied our Amazon model to an existing ozonation plant on a demo scale. And here you see 4 years of data. So a lot of bromate measurements measured at the effluent of the ozonation. And we modeled this 4-year data. And I wanted to show you this graph just to show you the power of a digital twin. So in orange, there should appear a beautiful graph. So yeah, you can see that the model really captures this dynamic data and predicts the bromate formation very well. And we are now actually building more and more of these digital twins of full-scale installations, where we are going to predict the micropollutant removal and bromate formation in real time. So measure in real time on the influent side, basic data, and the model will predict the bromate formation and the micropollutant removal in real time, so that operators can use this information to smartly control the system and have better performance. All right. I think maybe it's more interesting to skip to the conclusions than to do this poll right now. So Wim, I'm going to give the floor to you.
Peter, thanks a lot, Peter, for bringing this up. So I would invite everybody to ask a couple of additional questions. So after the conclusions, we can continue a bit with the remaining questions and answers. So that's always exciting. Okay, let's go to the conclusions of this webinar. So we try to hit a couple of key points. Of course, there are many more key points, but to us, if you look at the current practice, what is happening, for example, in Europe and in certain countries, for example, Netherlands, Sweden, these are countries that are going quite hard now on ozonation. But you had, of course, also Germany, you have Switzerland, and a couple of others in Europe. And then, of course, you have the US. All these things are very important because we are talking about effluent, and effluent is highly dynamic. And the first key point was matrix makes design and operation very challenging. So this is what Peter talked about. We have dedicated webinars from the past on this, so you can watch the movies again. But ammonia was one example that was touched upon, and it has really a big impact. Same with DOC, your organics, it has a big impact. Then, of course, the second key point was the scale up. So pay attention if you scale up from batch to a pilot or from a pilot to a full scale, that there are also assumptions in how your design of experiments was, how your experiment was set up. So pay attention to that. It's not only the water matrix effects. So water matrix is your water composition. So also your design. Then if you ultimately decide to build a plant, your design choices really matter. So pay attention how you put your diffusers there, how you size your compartments. And if you really need so many baffles, and if you really need that size of a plant, because you can take into account the dynamics in very good ways. And then the fourth one was more with regards to the operation. Dynamics are very obvious. So this is what Giacomo has shown in his simulations. Everything fluctuates a lot, and it's not only the sewer network, it's not only the season or the weather, it's also how the plant is operated. It's also how much industrial discharge versus municipal discharge you have on your plant. All of these things cause dynamics, and by understanding them, you can actually smartly operate your plant. And this is what we are really focusing on a lot on with a lot of customers. So yeah, also the models are available. Of course, we have been working on this for 4 years, so it's not a small amount of time, but now this model has come to a state where we can help a lot of customers with our services. So they just ask us to run simulations for them to help with virtual piloting, conceptual design, detailed design with the CFD included, and also digital twins. So the last application Peter talked about, it's really rapidly emerging. A lot of plants are now thinking about implementing a digital twin. So a virtual plant that runs in parallel with the real plants. So that virtual digital twin predicts variables you cannot measure based on things you can measure. And that's really the core concepts. And that in ozone, it's about bromate and micropollutants, especially, for example. Then CFD Amazon is extremely powerful because we are now, we have come to a day now in time where we can simulate bromate formation in 3D. And this really allows for the next level ozone reactor design. So any requests or questions you can always send to solutionsteam@amteam.com. So please contact us, don't hesitate. Well, we have an additional time, 10 minutes left or 8 minutes left for Q&A, questions and answers. So we invite everybody to bring up questions. If you would decide to leave now, please fill in the questionnaire because we really want your feedback. And please contact us for questions at solutionsteam@amteam.com. We can also share some of the papers we have been referring to, and you can watch our recordings of past webinars and this webinar as well on our YouTube channel. Yeah. Okay. So I'm asking Charlotte if there are additional questions to be answered. Charlotte?
Yes, Wim. In the meantime, we got a couple of more questions coming in. So one from Struan, I hope I pronounced that correctly, on digital twins, because there are some different explanations for the concept, let's say, but you briefly mentioned it. But could you expand a bit more on the concept and what it exactly is in our definition?
Yeah. Yeah, indeed, a very good question. So I can say one thing. So we attended the WRR Mod conference, which is a joint conference between IWA, so the International Water Association, and WEF, which is the American Environmental Federation, the Water Environmental Federation. And at this conference, there was a big discussion happening. How should we define it? And the conclusion is there's no clarity around the definition yet. So we still have to search for it. Yeah, but it all comes down, of course, to having a model that is a digital copy of a real plant. But the big discussion is going on is a digital twin only a digital twin if it runs in real time, or if you do an offline simulation, for example, the one we have shown for a couple of plants, is that also a digital twin? According to us, a CFD model is also a digital twin. So it's a digital copy that is a 3D copy. In our definition, if we talk about digital twin for Amazon, we talk about the real-time application of Amazon running in real time with the plants, giving predictions on bromate formations, on a huge amount of micropollutants in real time, things you cannot really measure in real time. To our definition, that is really a digital twin, because you have the real twin, your existing plants and your model. But the digital version of your twin can be born first. And that's a bit, so it's not the twins, it's not like with humans or animal species where they have to be born at the same time. They can either exist one or the other first. That's a bit our definition.
Thank you, Wim. I hope that's clear to everyone. Then another question from Jacob. Can you, based on the influent water, simulate ozonation transformation products in the effluent water?
Yeah, so the biggest transformation product or byproduct we are focusing on is bromate, because that was of the biggest concern and that was the biggest pain in the industry. That's why we have focused the model first on that. If you talk about other transformation products, either it can be, for example, if you're breaking down diclofenac, which is a pharmaceutical, and you're interested in the byproducts, we can include these kinetics. So the kinetics that are known for some pharmaceuticals, and we can predict the byproducts of them. That's one thing that is on our agenda for the future. Another thing is other byproducts, for example, an increase in toxicity due to, the formation of aldehydes or ketones. So these are organic molecules. I'm now really going into detail, but if you oxidize humic acids, so these big molecules which cause the yellow color of effluent, this is causing the toxicity. The good news is they are biodegradable readily, right? So you can degrade them. But again, there a lot of interest there. It's on our agenda. We want to extend our Amazon model with that as well. It's currently not in there. And third, you have other things, for example, NDMA. NDMA is another byproduct that can potentially be formed out of fungicides, for example. You have certain nitrosamines that are causing NDMA formation if you oxidize them with ozone. Again, that is also on our agenda. Currently, our model is readily available for bromates. The other ones will be following in the future.
And then one last question maybe from Jose. What about industrial water with complex matrix?
Yeah, very challenging. Good question. Interesting, challenging. It's completely different. So ozone demand typically is way higher because you are talking about huge COD. So the DOC or COD, so the organics levels are very high, very toxic, very persistent. So ozone demand is huge. We have been asked by a couple of parties to also model that. And if the data is there, we can tweak our Amazon model to it. But ozone kinetics differ quite a bit. So, I mean, it's all consumed much faster. And it's very hard to measure a residual, for example, of ozone. It's a bit more tricky. But we can definitely look into it. One good example is pharmaceutical wastewater, where if the pharmaceuticals are known, pharmaceutical wastewater from the pharmaceutical industry, for example, that you don't have micropollutants, but macro, right? It's industrial wastewater with pharmaceuticals. If the rate constants and the concentrations of individual pharmaceuticals are known, we can predict or have a good estimation based on lab data.
Thank you, Wim. And then one last question to close the webinar from Mohammed. What is the difference between your digital results and real or experimental results regarding your modeling? To be more specific, how much errors, and can you expand on the accuracy of SUMO?
Very good question. Yeah, I maybe will go to Giacomo for this, or Roberta. I don't know, one of both maybe can answer this question.
Yes, that's a very relevant question, because there is a lot of uncertainty already around the analytical methods that you can use, for instance, to measure bromate. There are uncertainties around the sampling methods, the place in which you're going to sample in a certain installation. So we have seen hotspots for bromate production. So these are like overarching uncertainties. And when we compare that to the model predictions, then we should also include that concern around that. So what is the accuracy of SUMO around, for instance, the prediction of bromate or the removal of a micropollutant? That is, it's strongly related to the metrics and to the specific injection strategy that can have an influence on the final performance of the installation, and then also depending on the dynamics. So where you have like these higher peaks that we have seen and bromate formed, there can lay a higher uncertainty, both on the experimental side, but also on the modeling side. So we try to consider all this picture and then include that in an uncertainty band that we put together with our bromate predictions, for instance, or micropollutants prediction. Peter has shown some graphs of long-term dynamics of bromate that were going along with a shaded area. Those are like including the uncertainty for that specific case. We can not extrapolate to all cases, but for this specific case, based on the batch tests that were behind the whole study, we could extrapolate the uncertainty around that. Yeah, it's a very relevant question. Thank you.
Yeah, so to add a bit on that, we are more and more adding these uncertainty exercises in our modeling. So there's an uncertainty in the data, there is an uncertainty in the model calibration, and we are trying to feed them all into the model. And then you have to run, it's a specific technique, it's called Monte Carlo simulation. If you, that's the uncertainty analysis Giacomo is talking about. You run a lot of experiments and then you plot the statistical uncertainty interval. So more and more we are working on that to get a better view on this. Yeah.
Okay, thank you. We have no more questions at this point. Perfect.
Yeah. So then all that remains is to thank everybody for the very good questions, for the attendance, engagement, and also to my fellow presenters. It was again fun. And we really hope to see you in one of the upcoming Amazon webinars. If you have suggestions for topics, let us know and email. We will try to address them. And this webinar series will continue forever, for eternity. So see you again next time. We are ready for that. Okay, thanks a lot for your attendance. We will close it here.